Hi, chemistry students. We're on Unit 8, PowerPoint number 2, Shapes and Polarities of Molecules. And in your notes, you'll find this, and you can work with this as we go through. I'm also hopefully going to pop up a little bit more to show you some models, okay, like this one. And we'll see how it goes. Okay, so we'll start out with PowerPoint number 2. Here we go. Slideshow from the start. Okay, PowerPoint number 2, Shapes and Polarities of Molecules. Here we go. So first of all, as we talk about shapes of molecules, I want you to realize that there is an important reason we talk about shapes. Many of the physical and chemical properties of compounds depend upon the shape, or we sometimes call it the geometry of the molecule, and also its polarity. And polarity just has to do with whether it's has a sort of positive and negative end. A very important example of how shape can really be life-changing is the shape of the hemoglobin molecule. Hemoglobin is in your red blood cells, very important in terms of absorbing iron, but also important to that it's at the proper shape, because if it's not, you develop something called sickle cell anemia. A normal red blood cell, you can see, with normal hemoglobin, goes easily through the blood vessels. But someone who has the mutation for sickle cell anemia, the abnormal hemoglobin has a different shape, and it makes the red blood cells into these sort of sickle shapes. The sickles can then block the blood flow. They can do all sorts of things. They can cause pain. It's a very chronic condition. You'll need blood transfusions throughout your life. About 1 in 500 African American births, children have this mutation, and it's a lifelong chronic disease that can cause premature death. So the shape of the hemoglobin molecule is what makes the difference here. So molecular shape can be very, very life-changing and important. So first of all, I mentioned the word polarity, and that is what you have where you see molecular geometry levels of sharing. So what is polarity? And I want you to think of sort of north and south pole. Polarity is like the North and the South Pole. They're different. On the North Pole, you have polar bears. On the South Pole, you have penguins. You can tell the difference between the ends. Molecules are the same way. If you can tell the difference between the ends, then you have a polar molecule. So why does this occur? When nonmetal elements, and again, we're only talking about nonmetal elements, covalent bonds, have different electronegativities, they fight over electrons. So they share, but they share unequally. So the more electronegative element is more attractive to the electrons, and so they stay closer. So there are a couple of levels of sharing. Instead of just being covalent, where we share electrons, and ionic, where we transfer electrons, there are actually 3 levels of sharing. There's something called non-polar covalent. That's where the 2 atoms in the shared bond are essentially the same, have the same electronegativity, the same attraction for electrons. So that's when it's like you and your twin brother, who you get along with, sharing a cookie. You share it equally. It stays in the middle, and that's what this shows, is the electron stays in the middle equally. That's called nonpolar. I can't tell the difference between the ends. The next one is called polar covalent. Okay, so nonpolar means I can't see the north and south pole. Polar covalent means I can. It means that one of the atoms in the bond, in the shared bond, hogs the electron. So we share unequally. The one that is more electronegative is going to hog it more because it's more attractive to the electron. The one that's less electronegative is going to hog it less. So you develop a partial positive end and a partial negative end. So it's not as strong as having like a positive ion and a negative ion, but there's a partial positive and partial negative end. And then ionic is a complete transfer. So in other words, the positive has completely transferred. You can see there's no sharing in between, so it's ionic. So we really have 3 types of bonding: covalent, polar covalent, and ionic. So covalent bonds can be, so just going back here, you ought to write this into your notes. So the first one you should write the picture beside it, non-polar covalent. The second one you should write, we have the partial charges, polar covalent, meaning unequal sharing. And the third one you should put a positive and a negative, and that's ionic. All right, so then we're going to fill in the blanks. Covalent bonds can be classified as either polar covalent or non-polar covalent. So and you should write in polar covalent bond, electrons are more attracted to the atom with the greater electronegativity, resulting in a partial negative charge on that atom. The atom with the smaller electronegativity value acquires a partial positive charge. So there are ends to this bond. In a non-polar covalent bond, and that's the second blank, the electrons are shared equally, and there is no unequal distribution of the charge. Okay, so how do you tell the difference? So you have this little chart in your notes, and you can see this one we call pure or non-polar covalent. So these are the two atoms that are sharing, and we essentially say if there's an electronegativity difference of between 0.0 and 0.4, and again I have to give you those numbers, but if it's the same atom then it's going to be 0, and then this 0.4 is an acknowledgement that the carbon-hydrogen bond is their carbon and hydrogen are so close in electronegativity that we consider them sharing equally. So that's non-polar covalent bond, they're shared equally. In a polar covalent bond, they're shared unequally. So that's between two non-metals, and the electronegativity difference will be between 2 and 0.4. Now, if you have a metal and a non-metal, you'll notice every single time the electronegativity difference is going to be really big, between 2 and 4, and that's going to mean that they're not sharing at all, that the negative is in control of the electron, the positive doesn't have it at all. So that's what that picture means. So again, it's always nonpolar between diatomics. Another prominent nonpolar would be the hydrogen-carbon bond because it's only a 0.4 difference. Notice carbon is 2.5 and hydrogen is 1.5. You'll notice between ionics like fluorine and maybe lithium, it's a huge difference, 4 to 1, so that's 3, so that's an ionic. But between something like oxygen and nitrogen, it's only 0.5, so that is going to be polar covalent, unequal, but it's not so big that they're not sharing. Okay, so again, partial positive, partial negative, depending on the electronegativity. We sometimes draw the atoms, the bonds like this. Here's another one between hydrogen and bromine. And bromine is much more electronegative. We can see the difference in the ends between the two. This is more electronegative than hydrogen. If you go back, let's go back to our chart. Let's see, bromine here is 2.8, whereas hydrogen is 2.1, so you have a 0.7 difference. So it's going to spend more time close to the bromine. And so that's why you have that negative charge here, because the electrons are being hogged by the bromine and not so much by the hydrogen. Okay, so that brings us to this, VSEPR. It's called VESPR. VESPR, say that in your mind, VESPR, valence shell electron pair repulsion. So again, repulsion means I don't like you. Valence shell means those 8 electrons in our dot structure. So the geometry of a small molecule can be predicted by examining the central atom and identifying the number of atoms bonded to it and the number of unshared electron pairs surrounding it. The shape of molecules may be predicted by using this VESPR rule, which states that electron pairs around a central atom will position themselves for the maximum amount of space between them. So those 4 bonds that we see in the 2-dimensional drawings are going to be as far apart as possible. So we don't just name the shapes willy-nilly. We have 5 shapes that we have to know the names, and we have to know what atoms form those shapes. And again, we're just looking at very small atoms, very small molecules with 1 or 2 central atoms. Okay, so let's have a little bit of a show and tell here. So first of all, if you turn to the second page, you're going to see a chart that you're going to fill in. And let me come back. So the chart looks like this, okay? And I want to just show you the difference between polar and nonpolar. So in a bond, if this is H2, this is non-polar because you can't see the ends. The electronegativity of each hydrogen is the same. So it's a non-polar bond. I can't see the penguins and the polar bears. On the other hand, that HBr we saw was more like this. Here's the bromine, here's the hydrogen. You can see the difference. You can see the poles. I can see the polar bears because there's no more ice in the Arctic, and I can see the penguins, right? That's polar. It's lopsided, okay? again, we're looking at small molecules. So the first one we're going to look at is one that is diatomic, linear. So we're going to fill in this chart here, and I'm going to show you some pictures. So let's go back to this. Oops, that's not the one I want. This one. And play from this slide. So there's no central atom. These are diatomic molecules. So in the first column, you're going to write no central atoms. The shape that you're going to write in the second column is linear, and there's no bond angle. If it's a line, there's no real angle. If there's just two atoms, to have an angle, you have to have three for that. Essentially, linear molecules are nonpolar if the atoms are the same. So any of the diatomics, okay, so in where it says molecular polarity, you can say it is nonpolar if the atoms are the same. And it's polar. We can see the ends if the atoms are different. Okay, so that's the first row. Now we're going to do the next row. This is where we're talking about three atoms bonded. Okay, so you'll see in the second row it says atoms, areas of shared electrons on the central atom. So another linear molecule is two shared bonds and no unshared atoms, areas on the atom. So underneath you should write that would be a central carbon with two double bonds, could be two double bonds, or a central carbon with a single and one triple. Okay. In the second column, you'd write linear molecules, and the bond angle would be 180. It's nonpolar if the bonded atoms are the same, and it's polar if the bonded atoms are different. And again, slow down this video if you need a chance to absorb this, but here are the Lewis dot structures that you wrote, the 2D pictures. But you can see that we want these areas of sharing as far apart as possible. So that would be 180 degrees, 180 degrees. 180 degrees. Again, let me show you the models here to give you a sense of why that is so. Okay, so all right, so here is CO2. And again, on the models, you can see these bonds look a little bit bendy, but that's just because we can't move the holes. Carbon has 4 holes. We have the 2 oxygens here, double bonded. Okay, and you can see if you just sort of ignore these things, the shape is just a line. And again, it can't be bent because that would bring these electron pairs closer together. Here's one with a HCN with a triple bond and a single bond. And again, the idea is that we don't want to bend this because that would bring the electrons closer together. It's 180 degrees straight line between the 3 atoms and the bonds. That's a linear molecule. So carbon with 2 double bonds or carbon with a single and a triple. There are no unshared electrons on the central atom. We're just talking about the central atom. Okay, let's go back and play from the current slide. So that's the second row. Okay, now let's go to the third row. Next shape. Okay, this is something called trigonal planar molecules. This is where there are 3 shared bonds and no unshared electrons on the central atoms. Underneath, you should write central boron with no double bonds, or with no bonds, and central carbon with 2 single and 1 double bond. Okay, so weird thing about boron is that boron is an exception just like hydrogen. It's happy with 6. Again, the idea is boron is an exception. Instead of being happy with 8, boron is happy with 6. So it makes just 3 bonds. As you can see, the bond angles are going to be 120 degrees, and because that keeps them the farthest apart. There are no electrons, no pairs on the central atom. Again, we're only talking about the shape around the central atom. This shape is nonpolar if the atoms are the same, like in BF3, but they're polar if they're different. Because again, look at this. This carbon has 3 areas of bonding, and it's got a double and 2 singles, and that's going to be the farthest apart it can be. To make that the Vesper model stick. We want these areas as far apart as they can be, and that's going to be a flat 120. Okay, again, let me just show you real briefly. Model. or two models. Okay, so here is the trigonal planar. Okay, this is the boron. Notice boron's happy with 3. It's just flat, and it's a triangle, and it's because it's a triangle, it's 120. Here is the formaldehyde that we did, the HCOH. You can see it's got a double bond. It's still flat, though. There's no extra electrons on the carbon, so it's a triangle shape. So a carbon with like in this configuration with a single and two doubles is always going to be trigonal planar. Doesn't change. Okay, so let's go back from the current slide. So again, you have 3 areas of bonding, and you just have to remember boron has no double bonds. It just has 3 single bonds. Moving on. Oh, so and again, this one would be nonpolar because it's symmetrical all the way around. This one we can see the ends. We can see the polar bears and the penguins, so that one would be polar. Okay, next line, we're getting down there. We're on the 4th row, are tetrahedral molecules. That's the shape you're going to put in the second column. This is 4 shared bonds and no unshared electrons on the central atom. This is just going to be a central carbon with 4 single bonds. Now, usually we draw it flat. I want you to notice how to do these 3D pictures. You can see that if you're going away from the plane, you do dots. If you're coming towards, you're doing this line towards. Again, it's not just a flat two-dimensional like we've been doing before. This shows CH4. The bond angle is 109. It's nonpolar if the atoms are the same. See, we can't really see the ends. I'll show you that in a minute. And it's polar if you can. If it's CH3F, we can see one side is more lopsided. And in fact, this is going to be the negative end because the fluorine is very electronegative. So let me again show you some models. So notice this is not flat, CH4. This bond angle is actually 109, and that's to keep these things as far apart as they possibly can. If you just draw it as like a flat square, then they would be closer together. If you put it at 90 degrees, that would not be the correct shape in 3 dimensions. So when you draw it, you have to indicate that, you know, one's kind of coming out towards you, one's going away, one's sort of in the, 2 are sort of in the plane. This one is non-polar because I can't see which end is which. I can flip this and you would never know. On the other hand, if I have CH3F, I can always tell which end is which. That means that it has poles, it's lopsided, and it's polar. Okay, so let's go back. Not that one. Here we go. And play from the current slide. And use slideshow. Again, this one would be not polar. We can see the ends, but notice how we indicate the 3D shape. This one would be polar. This one right here would be polar because we can see the ends. Last 2, we have bent. 2 shared bonds and 2 unshared bonds on the central atom. And again, this is what the shape of an oxygen is and its family. Here are the 2 non-bonding pairs. The bond angle is actually 105. This is sort of looks like a tetrahedral, except 2 of the areas have non-bonding electron pairs. It's always polar. We can always tell the end. Okay, and again, if you get a water molecule, here I am with my water molecule, you can see it's not symmetrical. I can always tell the end. It's not going to be, sometimes we draw it kind of straight out and flat, but it's not going to be that way. And that's because you have these non-bonding pairs, and they are just as repulsive as the bonding pairs. And therefore, it's going to have a shape. It's kind of like, you know, if you hold it up against the tetrahedron here, okay, whoops, like that, you can kind of see that you have the areas where the tetrahedron has a bond in the carbon, they're just non-bonding pairs. So it's a bent shape, and that's always polar. Central oxygen, always bent. All right, we're almost done. Got just one more shape to go. This down here. And we'll say play from the current slide. Okay, so it's always polar. Always, always polar. Final one is something called pyramidal, and occasionally you will see it called trigonal pyramidal. That's why it's important that you put either trigonal planar or trigonal pyramidal. It has 3 shared bonds and 1 unshared pair on its central atom, and this is going to be nitrogen. Nitrogen has that unshared bond, and then here are the 3. The bond angle is 107. It's always polar because it's not symmetrical. I'll show you this one too, and then we'll be done. So here is NH3. Now this time I put the non-bonding pair sort of as 2 dots at the top. So these bonding pairs are really repulsed by that. They don't like that. So it's not going to be flat. Notice the difference with the boron. There's no dots on the boron. There's nothing to repulse it to come and bring it down. Notice this one looks a little bit more like a pyramid. Sorry, look like a pyramid. Whereas this one is entirely flat. Okay. So again, the shape around a central nitrogen is pyramidal. This is again sort of a memorization thing. Central nitrogen, always pyramidal. Central oxygen, always bent. Central boron, okay, always trigonal planar. Now carbon is tricky. If carbon is bonded to 2 things, it's linear. If carbon is bonded to 3 things, it's trigonal planar. Okay, if carbon is bonded to 4 things, it is tetrahedral. Should give you kind of a hint. 2 things, linear. 3 things, trigonal planar. 3 things. 4 things, tetrahedral. Okay, so now you're going to build some molecules. Okay, you're actually going to build some molecules, and you're going to practice these shapes and use the chart to practice the shapes. So you've learned them all, and good luck, and that's the end of the show.